All right, so today we are going to begin to cover one of the most important topics of this class, and that is fatigue failure. And we'll just give an introduction, talk about some of the theories, its importance, etc. today. Fatigue is also associated with dynamic failure, where we have dynamic loading, which is loading that has varying amplitude of forces, not just a static load. So we need to treat systems that experience loads that fluctuate as dynamic loads. And in fact, dynamic loading is responsible for an estimated 90% or more of machine failures. As such, it's a big deal. And this lecture is one of those where you need to make sure you understand every slide, because there's a lot of detail and there's a lot of caveats, and it's a very, very important topic. Anytime we have time varying loading, we have to design against this failure mode, this fatigue failure mode. The term fatigue failure is actually somewhat of a misnomer, and it's accredited to Poncelet in 1839, where he indicated that material got tired and became brittle. We now know that materials don't get tired. They fracture due to cracks that originate and then propagate and then catastrophically fail. In 1982 dollars, the estimated cost of fatigue failure was about $100 billion, or 3% of the gross national product. So we need engineers that can predict fatigue and design against fatigue. Okay. What we talk about in this class is going to help you design systems, but cannot replace in situ testing for many machines. Okay, so even to this day, a lot of money is spent on breaking things people make to make sure that they don't die in the field. Now, a little bit of history. It was actually in the 1800s when steam-powered machines such as trains experienced this unexplained, at the time, failure mechanism at stresses that they knew were well below the yield stresses of ductile materials. And these ductile materials were failing like brittle materials. And so it really left people confused, since there really wasn't any theory that could predict failure. And yet these rail car axles were just suddenly catastrophically failing. Okay, we now know that it's because of time varying bending stresses, even bending stresses that are well below the strength of that material. So August Wohler spent over a decade studying this phenomenon with axles. And his axles were subjected to what we call fully reversed loading. Okay, and that's where we have a positive and then negative load, and it's easy to do in a rotating machine with a suspended weight. And he discovered that failure was related to the number of cycles. In fact, he also discovered that at certain fully reversed loads, below a certain threshold, resulted in the specimen that wouldn't fail in the steel axles he was testing. And that's where we came and first discovered this concept of an endurance limit of a material. And at that endurance limit, that's where the material, if you keep those cyclical loads below this endurance limit, which is a stress, then the materials will survive dynamic loading indefinitely, as far as we know. And the endurance limit it does show up in steel materials, but it doesn't show up in all materials. For example, aluminum does not have an endurance limit, and some other wrought materials do not have an endurance limit. And so we have to pick an effective endurance limit for those materials. His work is summarized in what we call a Wohler diagram, or an SN diagram, which is the strength and number of cycles. Okay, and that's what this diagram looks like. So over here, we start off with the ultimate tensile strength of the material. And then on this axis, we have the number of cycles. Okay. And if the material experiences and this is your failure lines. Okay. So at, let's say, 100 cycles, if you're below this line here, then you're okay. If you're up here, then your material will fail. And for some materials, like steels, like we said, there's this endurance limit that exists, so that if we're below those stresses all the way in this region, then the material will survive very, very, very many cycles. Okay. Other materials don't show this endurance limit, like aluminum. Okay, so you definitely need to remember those. But also magnesium, copper alloys, nickel alloys, some stainless steels, and some high-strength carbon and alloy steels. So you can't just say, steel has an endurance limit and aluminum doesn't. Well, aluminum doesn't, but you can't say that because you have to consider some stainless steels and some high-strength carbon and alloy steels also do not have an endurance limit. Okay. But that, fortunately for us as the designer, a lot of low-strength carbon steels and alloy steels, some stainless steels, irons, molybdenum alloys, titanium alloys, and some polymers actually do have an endurance limit. Okay, so anytime we have dynamic loads, we really have to get back and consider the materials, and our responsibility as a designer is to make sure that whatever we design is going to last for its intended life cycle. So when we talk about loading, we have these different classifications of loading. Okay, so this is the stress on some part that you're loading, and if the stress goes to a certain value and then comes back to the negative of that value and then back up to the positive value and back and forth, we call this fully reversed stress. And this is what Wohler did his tests on this case here, and I'll show you the machine that he used to do this here in a few slides. This stress state here is called repeated stress, and that's where we have no compressive stresses, no negative stresses. We just have a positive stress that goes back into a positive stress, comes to zero, goes back, and goes to a positive stress. And then we also have what's called fluctuating stress, and then fluctuating stress is where we have a non-zero mean stress and then a cyclical stress superimposed about that mean stress. Okay. So we have fully reversed, repeated, and fluctuating stresses, and these are the classifications that we use for dynamic loads. Now, another bit of history, the world's first jetliner was the British Comet, and then two of them fell out of the air within a few months of each other, and so it was very perplexing, and they wanted to know what was going on, and they went to great lengths to figure this out, and they filled the cabin with water to simulate pressurizing the cabin while in flight. The loading, the cyclical loading they determined caused cracks to grow at the windows, where the sharp corners caused stress concentrations, and these small cracks, which they said were less than 70 thousandths of an inch, caused these aircraft to fall out of the sky. And so you can imagine, the investment, the time, the loss of life, everything that goes that is affected by these small details that are all really design details and understanding of the materials. We have in our arsenal more tools now than we ever had in history to do excellent design, and fatigue is one of those things we have to care about. Now, let's talk about the failure mechanism. Okay, so the failure mechanism is if we have here, this is just some metal rod, and in this metal, if we zoomed way in, we see we have some grains, and we have grain boundaries, and we have imperfections in the material. And what happens when we have fatigue? It occurs due to cracks in 3 stages. Okay. The first stage of fatigue is crack initiation. Okay, because of these imperfections in the material, either they're real material imperfections or they're damaged material. they cause microscopic stress concentrations, which cause the material to locally yield due to high stress. So that's shown here. Okay, so if we have a tiny little crack that has initiated, and then we zoom in on that very, 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 very tiny crack that you may not even be able to see with your eyes, when it experiences loading, the crack tip, at the crack tip, it's a sharp point, and you have extremely high stress, okay, at that tip, which causes deformation. There's basic mechanics, and then that deformation causes that crack to grow and blunts the tip, which can kind of help, mitigate its propagation. But then under a cyclical load, again, it causes that crack to deform and grow. And then when it comes back down, you have elastic recovery in the material, which opens that crack up again. Okay. So these loads cause these cracks to have these localized yieldings due to these really, really high stresses, because it's, the force over the area, and at the tip, the area is really, really small. And this causes distortion, creating what are called slip bands along the crystal boundaries of the material. So as the stress cycles, that process repeats. The slip bands can merge into microscopic cracks. And then when the stresses exceed the yield stress of the material, that's what happens. Those cracks will grow. Okay? Ductile materials tend to develop cracks slower than brittle materials, and almost all materials, nearly all materials, have microscopic cracks. Okay? So when you have tensile stresses, they cause crack propagation. Now, crack propagation is the second stage of fatigue. Okay, and fatigue is a failure mode. When cracks propagate, this would be most of the life of the part. It's when the crack grows, and when that crack grows to the high stresses at the tip and it's relieved, the elastic recovery of that material actually causes that crack to open again. Okay. So then that process repeats. If we have corrosion, or we have materials in a corrosive environment, okay, then a crack will actually grow in the presence of static stresses, because that corrosion can cause the material to be eaten away if it has access to it, and it will cause that crack to grow. Okay, that's called stress corrosion or environmentally assisted cracking. This is a big deal. That's why materials that are sensitive to corrosion have to be coated, have to be protected, painted, treated, etc. Corrosion fatigue is what we call a part that's loaded in a corrosive environment, and the crack will grow significantly faster. Okay, and then finally, the last stage of fatigue is fracture. It's sudden and catastrophic, and when the crack grows to a point when the stress intensity factor equals the fracture toughness of the material. Remember, the stress intensity factor is what we associated with the crack. We talked about that before. It's not the same as the stress concentration. When that stress intensity equals the fracture toughness of the material, then that result is sudden failure. Okay. Okay. These are some examples of the surfaces left behind from fatigue, and you can see here where these the cracks are growing in this material due to these cyclical stresses. Okay, so this is something that's rotating, and you can see that the cracks are coming on both sides, and then finally it ruptures. You can also see the patterns here of the crack propagation. So when materials fail, you can see, you can learn a lot about how they failed by examining their surfaces. And the nature of cracks is they show these little wave-like features when they broke it. These are some other images. So these are in tension, or tension compression for different shapes. This is unidirectional bending. This is reversed bending, this is rotational bending, and this is torsion. And so if you have a component that fails, you can take a look at it and you can match it to the different loading conditions to see the primary cause of failure. These lines here of these cracks where they grow and stop and grow and stop, these are what we call beach marks. Then when we get to some length here, when our stress intensity equals that fracture toughness, then it just fractures off, pop. It'll pop off, and then that you can see that in that different discolored region. Okay. So these are some of the images that we get, and as you can see, the presence of these stress concentrations cause the shape to change in the fracture mode. Okay. Now, when we talk about fatigue, we separate fatigue into low cycle fatigue and high cycle fatigue. So low cycle fatigue is usually less than 10 to the 3 cycles. Some authors use 10 to the 2 or 10 to the 4. And then we have high cycle fatigue, which is greater than 10 to the 3 that we use in this book. Okay, so we use 10 to the 3 in this book to separate between low cycle fatigue and high cycle fatigue. And we have the stress life curves that we use for high cycle fatigue. So if we have an application where we have a part and we know that it's going to experience dynamic loading of more than 10 to the 3 cycles, then we'll use a theory for high cycle fatigue. And we can use these theory to find out what the fatigue strength of the material is, or the endurance limit for that material, and then we can start to look at our safety factors. This method of analyzing a part is it's the one that we use in this class, but it's actually the least accurate if you use it as it is, and it has to be corrected using correction and safety factors. Okay, so we'll start with the stress life curves because it's something that's tractable for us to do the analysis on as practicing engineers, but we then have to modify that with correction factors, and we'll talk about those in the next class. Okay. There's also a strain life curve, a strain life failure model. This model can be used to model the yielding, the crack initiation, damage. It can take temperature effects, but it requires substantial computational analysis and is beyond the scope of this class. It's more of a advanced method of looking at the finite element analysis and other stuff that we don't talk about here. So what we're concerned with in machine design for this class is, we need to get to the back of the envelope design, get to the first order design, but then we need to be aware that there's other tools that we can use, and we need to know when we're in over our head, when we need to go into a better theory for whatever we're doing. But the stress life will enable us to do design for the majority of machines that we will design. There's also linear elastic fracture mechanics models. Okay, so these are a little bit more advanced. You can use this model to predict crack propagation when you already know that a crack exists. It's good for low cycle fatigue, finite life problems, and it's commonly used in tandem with non-destructive evaluation when in service, such as in the aerospace industry. And in that case, what's done is we basically sensors. They use sensors to instrument the structure and actually measure the strain and stresses in that component, and then use that to predict the life. Okay, and so for a lot of machines that have predictable cyclical loads, such as in rotation machinery, like automobile axles, etc., the stress life approach is suitable. Okay, like if you have a crankshaft that is going to run 100,000 miles, then you could say, okay, these are the loads due to the combustion events of the engine, and it's going to be about 2.5 times 10 to the 8 cycles. So the stress life works well for these kind of theories. For machines potentially experiencing low cycle fatigue, okay, such as transportation machinery, airplanes, ships, etc., where loads are uncertain. Okay, so like if you go through a rough storm in the ocean, the ship is going to experience like higher than normal loads, or if the aircraft goes through a hard landing or experiences turbulence, then the loading is not as well controlled as like an axle in a car, and extensive inspection and instrumentation data is required. Okay. This is an image here of, I think it's Boeing doing a structural test on their airframe. And this is sort of like what you might see like as a time trace if you're collecting that data. And as you can see, there's portions of where the vehicle's in service and then experiences higher than normal loads, and then normal service, and then maybe a storm or whatever like that. Okay, and so these loads have to be accounted for those particular designs. Okay, now we've already said that we have fully reversed, fluctuating, and repeated stresses, and we have some symbols that we use to describe those. Okay, so the stress range is the difference between the max and min stresses. And then we have the alternating stress, which we will use when we have alternating stress in this class. And that's the difference between the max and min stress over 2. That's the amplitude here of that stress cycle. And then we have the mean component. And the mean component is the average of the stress. That's this dashed line here. That's your mean stress. Okay, and when we have a mean stress and a cyclical stress, then we'll have a different point that we have to consider when we do our fatigue life calculations, and we'll need these stresses to get our safety factors. But we'll start off with the simplest case first. There's also 2 ratios that we have. One is called the stress ratio. It's the min over max stress. The reason we have, I guess, the min over the max is because if the min stress is 0, then we can get a stress ratio of 0. If it was the other way around, we would have trouble dividing by 0. So you can kind of keep that in mind. Stress ratio is the min over the max, and then we have the amplitude ratio, which is the alternating stress over the mean stress. Okay, so it would be this alternating stress over this stress. Okay. When the stress is fully reversed, okay, then a minimum stress is minus the stress value, and the max stress is the stress value. So we have R of -1, and A is equal to 0, because the mean stress in that case is divided by 0. Okay. When the stress is repeated, okay, in this case here, we have a amplitude of 0, a stress ratio of 0 and a amplitude ratio of 1. Okay, so if we have mean stress, it significantly affects the fatigue life of that component. All right. So how do we measure fatigue? Okay, so R.R. Moore came up with the Moore test machine, and it is a test where you have a 0.3 inch radius here. Excuse me. And this shaft is spun by a motor that runs at 1,750 RPMs. You have support bearings here, and you have bearings here, and attached to this you have a little structure where you can hang weights. Then you have your support bearing on the other side, and these are just hanging in air, and this shaft is spinning, and you have a counter over here that just keeps count of the number of cycles. So you can put your load on here. So if you look at the beam diagram for this, you have your loads here, your reaction loads, and you have your weight loads and your reaction load here. And the load is chosen such that you have 0 shear here in the middle. And because of that, you can control the moment. Okay, and so the moment will increase because it's the integral of the shear, and then it'll be constant in the 0 shear section and it goes down. So it's a really clever little machine to control this so that you only have pure bending. And in pure bending, we know the stress is the moment times the distance to the neutral axis over the moment of inertia for that material. Okay, and so what happens is it's spun up, it's loaded, and then when the load when the shaft breaks, then there's a drop switch. This disconnects and cuts off the motor and stops the count. And that's how we get our the fully reversed bending stress data. And most of the data that we have for materials comes from these tests because they're easy to do. But obviously this doesn't cover all machines, and so we have to modify the results that we get based upon different loading conditions. And this is the fully reversed diagram for that stress, where we have zero mean stress, we have our alternating stress, and then we have our delta stress between our min and our max stress. Okay, so that's the machine that's used. That's where most of the data comes. Okay, and this is the data that comes out of these tests. So this is from low cycle fatigue, is 10 to the 3 cycles, up to high cycle fatigue up here, which maybe we'll separate as 10 to the 4. And these are for steels with the ultimate tensile strength of less than 200 KSI. And as you can see, there's this band here of failure that occurs. And so this test data is the fatigue strength, which is a stress value, and it's normalized by the ultimate tensile strength. Okay, so at about 50% of the ultimate tensile strength is where we're getting close to where we have all these failure samples being above that line. Okay, so this tells us something, you know, right off the bat, that if we choose a fatigue strength that is half of the ultimate tensile strength, then, and if we don't exceed that for fully reversed loading, that we should get an indefinite life. Okay. So this is just talks about it. So this allows us to get a quick estimate for the endurance limits, and of course that's the stress, the fully reversed stress that the specimen can endure, and we can get that directly from the ultimate tensile strength. Now that's for steels that have an ultimate tensile strength of less than 200 KSI. Okay, and you know, for these fatigue tests, they're run until they reach a certain number of cycles, or they break. Okay, so you can imagine how long it would take. So at 1745 RPMs, it would take 40 days to do 10 to the 8 cycles, which is, you know, somewhere out here, 40 days. Okay. And the samples that don't fail, after the number of cycles, we say that they never fail, and that's where we get the endurance limit. Okay. At stresses below the endurance limit, the sample can theoretically run infinitely without failure. Okay, so there is an endurance limit for many low-strength carbon and alloy steels, some stainless steels, irons, molybdenum alloys, titanium alloys, and some polymers. Okay, aluminum, magnesium, copper, nickel alloys, some stainless steels, and high-strength carbon steels and alloy steels do not have an endurance limit. That means if they are continued to be subjected to cyclical loads at some point in time in the future, they will fail. Okay, and their fatigue stress continues to fall as a function of the number of cycles. Okay, now if the endurance limit exists and you have a material that has an endurance limit, for steels, okay, that have an ultimate tensile strength, low carbon steels with an ultimate tensile strength of less than 200 KSI, you can choose as a starting point an endurance limit that's 50% of the ultimate tensile strength. That's where this comes from here. Okay. Now, if you have steels that have an endurance limit and that are that have an ultimate tensile strength of greater than 200 KSI, then the endurance limit you would set to 100 KSI. Okay. Now, if you have notches which lead to stress concentrations, or you have a corrosive environment, then we have to use correction factors to adjust the endurance limit, which we'll call SE prime, to get an endurance limit that we use. And this graph here just shows the endurance limit. Okay, so this is the cyclical stress that can be endured by the specimen. It's, I think, fully reversed stress that would come from that bending test data. And you can see if we have a polished specimen, we're in this area here. Okay, and you have a wide range of area as well. Okay, so these are how long the specimens lasted, and in these, according to this ultimate tensile strength, this was their endurance limit. And I think for this chart, I think they were run to some certain number of cycles, like 10 to the 8 or something like that. Okay, now you can see what happens when you have notches which cause stress concentration. It dramatically lowers the endurance limit of the material. And in fact, if you have corroding specimens, you have no real endurance limit. They have a regime of failure that's very, very low. Okay, so corrosion is something that has to be protected against. Now, for the materials that don't have an endurance limit, such as aluminum, magnesium, copper, etc., their endurance limit continues to roll off, okay, as a function of the number of cycles. Okay, and because we can't run these tests forever, then what they do for certain materials, they try to get a fatigue strength that's at an established number of cycles. Okay, so when you have a number of cycles that it's 5 times 10 to the 8, that's the established value for the fatigue strength for these materials. Now notice we don't call it the endurance limit. We don't say there's an endurance limit for those materials. Instead we say, we have this fatigue strength. Okay, and this is what it looks like for different materials that don't have a endurance limit. Okay. Now, aluminum, like steel, has a fatigue strength that depends on its ultimate tensile strength. And for aluminums, what we can do is take a look at the fatigue strength at 5 times 10 to the 8 cycles. Okay. And it's about 40% of the ultimate tensile strength. Now remember, for low carbon steels, we said it's about 50%. And for aluminums, we say it's 40%. If their ultimate tensile strength is less than 48 kpsi. And that's what we get from these charts here. Okay, so for aluminums that have an ultimate tensile strength of less than 48 kpsi, they're along this curve right here, and it turns out that the fatigue strength, defined at 5 times 10 to the cycles, 10 to the 8 cycles, is about 40% of its ultimate tensile strength. Now the fatigue strength for aluminums that have greater than 48 kpsi ultimate tensile strength is 19 ksi. Okay, kpsi. So you can see here that the we have the similar cases, but the caveat is there's no these are not endurance limits like we saw in steel. These are fatigue strengths. Okay, here in aluminum. So these last few slides are very important to understand and make sure that you get some, you have these 4 values kind of like stuck in your head, okay, for aluminum and steel. Now, everything we talked about so far had to do with these fully reversed rotating bending tests from that R.R. Moore machine. When we have tensile stresses, though, they accelerate the fatigue crack propagation phenomenon and reduce the life. Okay, so the fatigue strengths are 10 to 30% lower in axial loading, cyclical axial loading, 10 to 30% less in, say, push-pull axial loading. Okay, and you can see that here. So these are your rotating bending tests up here. This is your fatigue strength versus cycles. Okay, and then if you put an axial load here, then the fatigue strength drops by 10 to 30%. And this is for a low carbon steel, a 1090 steel. So for axial fatigue, what we say is the fatigue strength is about 80% of the static strength at 10 to the 3 cycles and 40% of the static strength at 10 to the 6 cycles. Okay. So 80% of the static strength for low cycle fatigue, 40% of the static strength for higher cycle fatigue. Okay, and they're both 10% lower than the rotating beam data because we had about 90% and about 50%. Polymers also fatigue. Okay, so this is a graph of various polymers such as Teflon, nylon, epoxies, etc. Okay, and you can see here that they follow similar trends where you get into higher cycle fatigue and these materials fatigue. Okay. Now, that was the axial difference. What about the torsional difference? Okay, so tests were also done on cylinders that had fully reversed torsional loading. Okay, and this is the test data here, and it's normalized according to your principal stresses, sigma 1 and sigma 2, that are divided by your fatigue strength for that material. And what's interesting to note is that it looks almost identical to the distortion energy theories for failures. Okay. And it turns out that the torsional fatigue strength is about 57.7% of the bending fatigue strength. Okay, and that comes and matches, what we understand here, where we had, our shear strengths were about, 57.7% of our tensile strengths when we had specimens that were loaded in torsion. So this theory kind of lines up, which is pretty interesting, with the von Mises theory. Okay. Now, what happens when we have so everything that we showed so far is if we have a zero mean and zero alternating stress. So what happens when we have mean and alternating stresses in a material where we have some non-zero load and then some alternating load superimposed on top of that? Well, that leads to what we call the Goodman diagram, or there's also the Gerber line. There's also the Soderberg line, I believe is what it's called. But these are different theories that match the failure points when we have a mean stress and we have a alternating stress as well. So what we can do is calculate our mean stresses, and in this graph, the alternating stress is divided by the fatigue strength, and the mean stress is divided by the ultimate tensile strengths. Okay, so obviously when your mean stress is equal to your tensile strength, then you get failure. When your alternating stress is equal to your fatigue strength, then you get failure. All right. And then these are done based upon a certain number of cycles, like 10 to the 7 to 10 to the 8 cycles. Okay, for aluminum, for steel. Okay, this is for aluminum. This is based on 5 times 10 to the 8 cycles. Okay, so then what we can do, the way that we use this is we can calculate our our fatigue strength for that material. We can correct for it, and then we can calculate our alternating stresses and divide by those, and we can calculate our mean stresses that are present due to those cyclical loads, divide it by the ultimate tensile strength, and we get an XY point somewhere on this chart, okay, with the normalized alternating stress and normalized mean stress. Now, when we have that point, we have to be below this Goodman line because it's more conservative, so that's what we use. It's also a straight line, which is easier to just plug into the equations, but not much easier. And we get a point. So this is for steels. So let's say we had a normalized mean stress of 0.3 and a normalized alternating stress of 0.4. Okay, now the question is, well, how do we calculate the safety factor for this design? You know, how close are we to this line? Okay, now it turns out if the mean stress is going to change, but the alternating stress is not going to change, then the safety factor has to do with this distance. Okay, so if this is our calculated stresses, mean and alternating stresses, and we know the alternating stresses aren't going to change, then our safety factor is going to be a ratio of the distance to this line here if the mean stresses can change. Now, if the mean stresses are going to pretty much stay the same, but we expect the alternating stress, there's some uncertainty, then we'll take the distance to this line. Okay, that would be the shortest path to failure. Now, if both the mean and alternating stresses can both vary, then the closest failure mechanism would be a straight line to that point. Okay, we have all the equations for those. We'll talk about those in the next lecture. Okay, but it's important to understand where we are. So we've talked about the fully reversed stress, the fatigue life, endurance limit, the difference between steel and aluminum. And here we're talking about when we have a non-zero mean stress and some alternating stress on top of that. In that case, we need to use the Goodman diagram and use this Goodman line to make sure that we're below that so that we don't cause the material to fail. Okay. Now, this is a graph that shows us our alternating stress over the fatigue stress in both compression and tension. And this point here was where the data came from on the previous slide. This just shows the presence of compressive or tensile stresses. So if we have tensile stresses here, then we actually get failure, below the predicted failure. And if we have compressive stresses, we actually get improved life. That's also seen down here. This is just a graphic that shows, well, when you have 0% mean stress and you have alternating stress, that's the fully reversed stress. That's our normal line here. If we actually have compressive stresses, it gives us improved fatigue life. And that's why we introduce residual stresses in components. And we'll talk about that as well. If we have tensile stresses, that fatigue strength drops. Okay? We says 10 to 30% when we had the fully reversed axial loading. But when we have a mean stress in tension, then our fatigue life dramatically drops. Okay, so it's a different way of looking at that previous slide. And of course, this is when we have the state of fluctuating stress, non-zero mean and some cyclical stress. Okay, so we'll end the lecture there. This is a lot of material. This is probably, something you should read the book to complement your knowledge. I hope that this higher level discussion or sort of lecture about that can get you started. I encourage you to go through this material a few times because it's such an important topic, and there's a lot of new terms that we're going to be using. Okay.